Okay, welcome everybody. Thank you for joining us today. This is a little bit of an introduction to the CompuCell workshop that's coming up. I appreciate your interest in joining us for that workshop in August. The goal today is to help with teething trouble and get started. So if there are small inconveniences and issues, don't be discouraged. The point is to try to identify them today and make sure that everything goes smoothly when we get to the workshop proper. And feel free to ask questions in the chat. Don't be shy about asking questions in the chat. If you have a question, probably other people have the same question. And so don't feel shy about asking. We have Pedro del Castel and Hin Finel here with us today to help out with questions and problems. The slide deck is available online in the student materials folder. There's a Slack, which I encourage you to sign up for and use. And I need to remind you that the workshop will be live streamed and recorded and distributed. So this current session is live on YouTube at the moment. We want to thank everybody for their support. NIH and NSF have supported this project very generously over the years. So I'll go over the course logistics a little bit, answer any questions you have about that. We'll talk a little bit about background material that might be useful for you. We'll cover everything you need in the course, but it's helpful sometimes to have a little bit of a background. That makes things go a little more smoothly. So we will provide you with that information. And then we will do a quick exercise to try to get CompuCell teething problems worked out for you. And we'll talk a little bit about the hackathon. We'll do our best to support everybody. We have 150 plus people registered for the course. So please be patient. If you need help, we'll do our best to get to you as quickly as possible. If somebody happens to be an experienced CompuCell user and you'd like to help us out, we definitely could use that support as well. Let us know. So we're going to be talking in this course about modeling tissues, in particular multicellular organization. That could be in the context of development. How do tissues, organs, and organisms get built? How do tissues, organisms maintain themselves, homeostasis? Developmental diseases where homeostasis fails. The classic developmental disease is cancer, but there are many others. How infectious diseases work, how viruses and bacteria spread through the body, and how the immune system works to contain them and sometimes damage tissues, and how tissues redevelop after damage. Toxicology, how external toxicants can cause damage to tissues and how recovery happens. And then problems in drug design, optimization, therapy optimization, and in bioengineering, how do you build new things using biological components? These are all situations where you have a complex interplay between physical and biochemical control, and you can't understand these processes purely from a molecular point of view. One of the key characteristics about biology is that it covers a lot of scales. The key active agents at the tissue and organ level are going to be cells and what they do. And so the modeling that we're going to do is going to start at the cell level and move up and down. And so we'll have cells that are going to do things and interact with each other. They're going to have molecular control. They're going to exist in environments of chemical signals and mechanical signals. And we're going to be understanding how cells organize and cooperate to form complex functional structures. And so our simulations typically will have a level of molecular control, a level of cell behaviors, and then extracellular environment in which those things play out. Over the years, people have used CompuCell and related packages to do a whole variety of different simulations of different important biological problems. This slide illustrates a couple of new and old CompuCell simulations. At the top right, we have blood vessels in a tissue. We have a tumor that is initially non-vascularized. As the tumor grows, it will send out signals that induce additional blood vessel growth, which will lead to additional growth. And this process of neovascularization is one of the key hallmarks of cancer progression. The top left, we have a rare or genetic disease called polycystic kidney disease, where you have inappropriate cell proliferation, but no metastasis and no progression. In that case, we have a situation in which we get cysts. That work was done to try to understand the mechanisms of cyst formation and to try to identify drug targets for its treatment. In the bottom left, we have therapy optimization, where we're trying to study the use of photoablation therapy to treat diabetic retinopathy. Laser ablation therapy is damaging to the retina. It actually involves destruction of the retinal tissue. It's not always successful either. And so we were trying to understand how, in the case of individual patients, we could design therapies that were simultaneously more effective and less damaging to the retina. The right-hand picture is another computer simulation here of the retina. But in this case, we're looking at the growth of blood vessels where you shouldn't have blood vessels in the retina. That's called retinal neovascularization. In this case, this is a disease primarily of aging. You can have invasion of retinal tissue by vasculature, leading to destruction of the retina. Diabetic retinopathy and retinal neovascularization together are the primary ways in which adult blindness occurs in the developed world. In both cases, we're looking for new treatment options and treatment optimization. All of these simulations use CompuCell. CompuCell has also been used in the domain of toxicology. These are simulations from the U.S. Environmental Protection Agency, trying to understand how certain chemicals can disrupt embryonic development. In the first case, they were looking at chemicals that disrupt blood vessel formation in embryos. In the second case, they were looking at how hormone mimics, in particular estrogen mimics, can lead to genital disruption. That was a topic of great concern a few years ago during early development. And in the final simulation, they're looking at cleft palate. It's a birth defect in which the bones at the roof of the mouth don't close properly. It's a relatively common birth defect as birth defects go. And it can happen on its own, but it can also be triggered by toxicants in the environment. And so they were trying to understand the mechanisms by which environmental perturbations could lead to higher rates of birth defects. Again, these are all simulations using CompuCell. Some of them we may hear about in the breakout sessions in the workshop. This is a simulation of a viral infection in the lung and immune response. It was initially developed as a student project, but then published and further developed. In this case, we start with a patch of lung epithelial tissue. A single cell is infected. It releases virus. The virus spreads, infecting other cells. Those cells send out signals, cytokine signals, that call in an immune response. The immune cells then come, kill infected cells, which damages the tissue, because immune response always involves tissue damage. And we can understand effectively the competition between immune response and viral infection. And this, again, is a model that we use to develop rather a lot of simulations of antiviral therapies and much more detailed simulations of particular immune processes. So that's a direction one could go. There are many other examples we could find in the literature and from our own work of the kinds of things CompuCell can do. But I hope those examples, and we'll talk about these in more detail at the beginning of the class proper, but I hope that gives you some flavor for some of the questions you can ask with CompuCell. By the end of the course, I'm hoping that you'll be able to look at biological problems and have some intuition or understanding of what kinds of questions are interesting to ask, what can be answered with a quantitative simulation, like a CompuCell model. It's not always easy to come up with practical questions that one can ask and answer with modeling. Once you've decided what questions you want to ask, we have to be able to look at the biology, analyze the biological information, and map it into components and interactions that could then be turned into executable code. We then have to know how to translate that set of ideas into computer code, run it using the tools that we have, display it, and analyze it to derive biologically meaningful results. You could spend a lifetime doing this, but in a week, 10 days, you can learn how to do a lot of it. And the purpose of this course is to get you started so that at the end of the course, you're able to use these ideas independently in your own research. Just a little bit on course logistics. People should be free to ask questions in the chat. We have people here again who will answer questions as they come up. If there are major problems, we have 2 breakout rooms set up where you can go and get more detailed one-on-one assistance. We will post the Zoom links for the workshop and hackathon a little bit later. For now, for this set of orientations and also for the hackathon orientations, we'll use the current Zoom session. Since you're here, you were able to get into the Zoom. We will always have live streams on YouTube as a backup in case there's a Zoom problem. So you'll be able to at least watch the live streams as they're happening. It's a little more difficult to ask questions if you're using the YouTube links, but you'll have the Slack, so you can use that for real-time feedback if for some reason you can't use the Zoom. There's a hackathon discussion document and a hackathon Slack that Hayden will put in the chat for people as well. Zoom logistics, screen sharing and microphones will typically be disabled. If you need to use them, please request it. Do use the chat. If you have a question, probably other people in the room have the same question. So don't be shy about chatting with everybody. Of course, if it's something specific to one of the instructors or one of the other people in the class, it's fine to use private chat as well. Also, feel free to use the emoji icons, go faster, go slower, yes, no, hands up, these kinds of things. You're welcome to do that. We will use a variety of polls, in particular for completion. There's just a practical thing that sometimes we're not going to be able to have everybody do every exercise all the way through. So the key thing is to make sure that you get the basics done in the class time. And there'll be plenty of time to work on your own or with support outside of the regular class time. All of the exercises and results and examples will be available for you in the student materials. Videos and PowerPoints also will be available. For this year, the planned list of instructors is myself, James Glazier, Professor Gilberto Tomas from Brazil, Pedro Del Castel, who's here today to help us, also from Brazil, Giulio Belmonte from North Carolina State University, Jim Sluka, also from IU, Joshua Ponte Serrano, he's listed here as IU, but in fact he's at the National Institutes of Health at the moment, Priyam Adyapak from Duke University, TJ Sego from University of Florida, and Hayden Fennell, who's the course coordinator, also from IU. So we have a good team to support you and give the lectures and help that you'll need. The course will start with a little bit of time for open questions and concerns before we begin. Every day we'll start at 10 a.m. Eastern time. I know for people in Europe and Asia, that's not an ideal time, but there's no ideal time for everyone in the world. We appreciate people staying up nights if they have to, or getting up early. We will have 3 main modules per day. Each module will be 90 minutes. About half of that time will be lectures and ideas. About half will be exercises. This year, we're going to start to reduce the intensity and let people consolidate what they're doing. We're going to end every day with 90 minutes of intensive exercise work with support. So no lectures in that period of time. For people who are in strange time zones, if that's a bad time, we understand that people may not participate in that last module 4, but it's a great opportunity for people to get help and dig into problems more. We're going to have opportunity afterwards for some informal discussion and troubleshooting and questions with the instructors every day. The first week of the course will begin with a 1-day Python tutorial refresher for people. Then we will have 4 days of basic CompuCell. How do you build cells in a simulation? How do you control what they do? How do you design chemical fields and the interactions between chemical fields and cells? Which is the basics of tissue development. Week 2 will cover more advanced topics. We will talk about subcellular and macro networks, how to model them, how to integrate them with CompuCell cells, how to build cells that have subcompartments, structure for representing moving cells and epithelia. And then we're going to talk about links and building solids models with CompuCell. Some of the details of what we're going to implement still being worked out because there are a lot of different possible advanced topics. Then we're going to have a day when we talk about more elaborate models, and we're going to have some breakout sessions where some of the people who developed these beautiful models that I showed in those early slides will come and explain how they work. And then we'll talk about using Python in clusters, high-performance computing, and other advanced topics. Then we'll have a half day, third of a day hackathon prep, and then the 2-day intensive hackathon over the weekend. And we hope that many people will participate. You are not required to do advanced preparation. We will try to cover everything within the course itself, but in our experience, doing a little bit of advanced preparation beforehand makes the course work better. And so I'm going to talk about some of the things you might think about boning up on before the class, but you shouldn't feel that you have to do that, or that if you won't be able to do the class if you don't do it in advance. But these are advice. We will always try to be available to every extent possible to talk about your ideas, technical questions, scientific questions during the workshop. So I want to talk a little bit about background. I understand this is going to be a long list of things. Nobody comes to this class knowing all of the things that you need. Everyone has different sets of background. One of the things that is very valuable in a class like this is teaming up. For example, experimental biologist might team up with somebody who's a computational person, or a mathematician might team up with somebody who has more understanding of medical situation to learn from each other. So I hope people will use the Slack in particular to build teams where you can help learn from each other. Again, you don't need to know everything I'm going to talk about here. We'll cover everything that we need in the class, but it does go pretty fast. And so a little background reading in areas which are less familiar to you may make things a little smoother during the class itself. There are 5 real topic areas that one will need to build these kinds of models and apply them. 4 of these will be familiar names. One of them may be less familiar, and it's the one that I put first. You're not going to need to know any of these topics in great depth, but you will need to know a little bit about all of them by the time we're done. principles of modeling is the one that may not be so familiar as a name. Sometimes it's called computational thinking or mathematical thinking, quantitative thinking. And that is trying to understand what kinds of questions you can ask and answer with computational modeling. It's not always obvious what models can do to help you, what the value added of models is in a particular context compared to, say, doing pure experiments or doing pure mathematics. How do you describe a system? How do you analyze what its components are? What do you need to model? What needs to be included in the model? How do you define the model parameters? How do you measure them? What is the domain of applicability of a model? How do you build the network diagrams that are so important to understanding models? How do you validate or falsify models? How do you use models to understand mechanistic hypotheses or to explore what they mean to design experiments or to understand experimental data? These are things that we don't really teach in science courses. Engineering tends to teach this a little bit more than science does. But depending on your background, this may be a set of concepts that you've applied in biology, in science of other kinds, physics or chemistry, or they may be things that what you want to develop. Even if you never use multi-scale modeling again, learning to think about problems in this way will be useful in almost anything that you do going forward. You will need a little bit of Python programming, not a lot. We have a cheat sheet with basic Python, listing the various basic concepts that you'll need. We've got that Python day. It is important to have some familiarity with very basic Python. You're not going to need advanced Python, but if you have to learn all of the Python starting on day 2 of the workshop, it may be a little more difficult to keep up. And so we strongly encourage you to read the cheat sheet beforehand, play a little bit with Python beforehand if you haven't used it. And maybe it's worth just having a show of hands. How many people have done some Python programming? You can just use an emoji icon to say if you've ever done any Python program. So it looks like about half of the people have done it before. If you haven't done it before, don't be frightened. It's not so hard. But if you haven't, you might want to do a little bit of preparation. And then definitely do take that one-day Python introduction that we have at the beginning of our first week. What is it that you're going to need to be able to do? You're going to need to know basic Python syntax and indentation, because Python uses indentation rather than parentheses for block definition. You'll need to know the concept of loops, which exist in every programming language, but are a little different in Python. Logic and conditionals, which are basically the same in every language. Object types. In particular, Python has concepts of what are called lists and dictionaries. And these are very powerful data constructs that are not present in all languages. And CompuCell in particular uses the dictionary concept. And that's the one mid-level Python concept that we use quite a bit. You'll need to know a little bit about classes, scoping, and inheritance, although basically CompuCell will take care of those for you. And we need to learn a little bit about attributes and methods. You'll see a lot of something dot something else. And you'll learn pretty quickly what that means. But depending on your programming background, that may be familiar or not. Again, we're going to be teaching all of that in the Python Bootcamp. We encourage you to take that. If you're an experienced Python programmer, you don't need it. But that bootcamp will focus on the specific aspects of Python you need with CompuCell. And so even if you know some Python, it might be useful as a refresher. If not, That's fine too. Biology, we're going to be talking primarily about cell level biology and some about molecular control. And so a lot of detailed molecular biology probably you don't need, but basic questions like what are cells? What do they do? What are their behaviors? How do they interact with each other? When you're building a tissue, how does that work? Those are fundamental questions. Since we're going to talk about cell movement, you want to know how cells generate forces and respond to forces. We want to have some idea of how tissues are built, how they're constructed, what their components are, what their organization is. There are a couple of fundamental biological organizations. Mesenchyme, which is three-dimensional cell tissue with a lot of extracellular material and relatively few cells distributed in the environment. And epithelia, layers of cells, either single layers or multi-layers, where the cells are different on their top and bottom and side surfaces and strongly coupled to each other on their sides. Sheets of cells. We'd like to understand cell polarity, the concept of directionality of cells, and the second concept of cell planar polarity, which is an organization of cells that's perpendicular to the primary polarization axis. We need to know a little bit about extracellular matrix and how it's generated and what it does. We definitely need to know a little bit about how cells signal to each other, how cell metabolism works, and how cell regulation works. So gene regulatory networks and signaling networks are very important. Metabolic networks may or may not be important depending on the problems you are interested in. We need to know just a little bit about basics of chemical reactions and regulation in cells. We need to know how cell networks, like gene regulatory networks, relate to the things cells do, which is actually a big open problem in science as well, biological science. We might want to understand some of the basics of how blood vessels work, lymphatic system works, perhaps, if we're doing immune system, and how those relate to cancer and the special things that go on in cancer. And at a higher level, how biologists represent information. Biologists love diagrams. They need to be able to look at biological diagrams and understand them. We try to minimize the amount of physics and mathematics you need for this class. There are certain basic concepts that are important, in particular chemical diffusion, the movement of chemicals in the environment through diffusive processes is very fundamental to biology. The diffusion equation is down here on the right. If you've never seen the diffusion equation before, the key thing is that there's a chemical species, C, that diffuses, and a diffusion constant, D. This is how chemicals spread in the absence of flow. And it's a fundamental attribute of extracellular and intracellular chemicals. Another thing that you would want to learn about a little bit are the ideal gas law in springs and the general concept of a constraint, which may be less familiar. A constraint is something like a spring. A spring anchors the thing at the end of the spring to some distance from the other end of the spring. And a constraint fundamentally behaves like a spring, but in a very general sense. We'd like to understand diffusion length and diffusion time, how far a chemical gets in the environment, how long it takes to get there. Force velocity relations. If I push on something, how fast does it move? That's not so obvious in biological systems. Constitutive relations. If I push on something, how does it change its shape? Very important. The back end of CompuCell is something called cellular Pottsmall or GGH model. That has some idiosyncrasies. If we understand how it works, we can understand some of the limitations of CompuCell, debug its problems sometimes a little bit better, but it's not essential. If we want to understand that, we need to know a little bit about what's called statistical mechanics in physics. It's not essential, but these are useful concepts if you're going to go further. We need to understand a little bit about the role of fluctuations in biology. because fluctuations are critical to the way cells move and tissues organize. They're also fundamental to the robustness or lack of robustness of molecular signals. And some general biophysics can be helpful, although not essential. Mathematics, again, we try to minimize the amount of math that we do. If you're talking about networks, what are called dynamical systems theory is useful. Networks are rate equations. Those are first order ordinary differential equations, rate laws. It's helpful to know a little bit about partial derivatives, in particular the diffusion equation. Biology is stochastic, and the idea of the rates of transition is a useful concept. How do we represent chemical species and reactions mathematically? If you're taking Herbert Sauer's class, which is offered a few weeks ahead of ours in the summer on networks, that would be helpful, but it's certainly not essential for this class. And there's some fundamental concepts about mathematical stability. If I have a system that's in a steady state or quasi-steady state, and I perturb it, does it come back where it started? That's the concept of homeostasis. There's some mathematical ways of trying to analyze that. And if I have a simulation and I change the parameters, how does the simulation change? That's what stability analysis is about. Again, we'll cover everything we need in the class. You don't need a great deal of detail for any of these things, but having at least a passing familiarity with the concepts will certainly make things easier. And it's very unusual for anybody to come to this class and know all of these things. Think of it this way, sort of a Wikipedia level knowledge of these concepts is very helpful. You'll need to dig in more detail in specific things that you're going to work on in your own work. But to begin with, a little bit of each would be helpful. There are a lot of places one can go. Most of them give more information than you need. Don't be intimidated. But of course, having that material available when you need more information is useful. We need a better set of material on principles of modeling, I think. But at the moment, there's a paper that was written by a group of Canadian graduate students called 10 Simple Rules for Your Mathematical Model that's focusing on network modeling rather than agent-based modeling, but that is very readable and is a great place to start if you haven't thought about principles of modeling. We also have our own little guide to thinking about modeling that we distribute. We recommend, there are many, many online free Python tutorials. I particularly like the Rosalind Python exercises. There are plenty of good online materials and books, so you can find those, find one that you like. Again, you don't need to be a Python expert, but you do need to know what indentation looks like and what for loops look like and what a dictionary is. For network modeling, we use the Tellurium package. They're great online documentation. Tellurium is very easy to learn. And there's a great textbook by Herbert Sauer that's available for that. If you want to get a little bit more mathematical background, there's a book, Essential Mathematical Biology by Britton. That's a great place to look. It's elementary, but very, very readable and helpful. For biology, I find that Gilbert's Developmental Biology is the best place to start. I wouldn't worry about getting the newest edition, which is quite expensive and very long. You can get a 20-year-old edition online for $2 or $3. And the basic concepts are all there and it's not so detailed. So that's a great place to learn some basic biology if you're not so familiar with biological concepts. Again, Wikipedia has good things on most of these. For physics, there's the Physical Models of Living Systems by Nelson. It's an introductory undergraduate textbook that's very nice. If you really like biophysics, there's the Physical Biology of the Cell by Phillips, which is gorgeous, but it's quite advanced. But as a reference material, it's really unmatched in terms of its quality. There's also online Biology by the Numbers. It's a beautiful resource. which we should probably add to this slide now that I think about it, which is a database of numerical information about biological systems. It's very useful when you're building models. And we have a paper that I'll show again in a minute that goes into the background of the back end of CompuCell, how it actually does its computations. If anybody in the room has suggestions for sources or reviews that you think would be useful to add to this list, please let us know, and we'll let everybody in the class know about these resources so that they're available for everyone. Where to find things. CompuCell website is a primary point of reference. Downloads are in the website. There are online manuals, in particular the Python scripting manual is very useful. There's an old quick start guide, which you could work through. It's pretty old, but most of the things in it are still appropriate. We'd love somebody to help us update that to the newest release of CompuCell, if somebody wants to volunteer. We'll have the Slack channel for communication, the course Google Drive, and the materials will also be available on the website. That'll include all recordings, all slide decks, all exercises, supplemental materials, and so on. For Tellurium and network modeling, Tellurium readthedocs.io is the place to go. And there are a variety of quick reference guides, 3 of them in particular that will be used. The Slack is a way to help people interact since we're not physically together. It's really up to you to build community. I hope people will work together, find each other, find people with complementary interests, and build a community together. Of course, during sessions, you're welcome to ask questions in the Zoom chat. I encourage you to do that, but they do disappear. We capture the Zoom chats, but they're not going to be available to you after the end of the session. And so if it's something that should be in the record, gee, there's something that doesn't work and there's a fix for it, that really should go on the Slack, so it's persistent. If anybody has trouble joining the Slack, please talk to Hayden about that. We have 3 quick reference guides, a basic one for Python, basic one for CompuCell, and a basic one for network modeling in Tellurium. Those are things that I would recommend printing out. Having to flip back and forth between screens on your computer is a pain. So I would strongly encourage you to print those and have them on your desk when you're doing the class. I mentioned this 10 Simple Rules paper. I think it's a wonderful place to start thinking about modeling. There's this paper of ours about the back end of CompuCell and how it works. If you're interested in the biophysics of these methods, that's the place to go. Now, I'd like to talk a little bit about the hackathon. I hope people participate in the hackathon. You certainly don't have to, but we would love it if you would. Our goal is to try to organize effective teams. In our experience, teams of 3 to 6 members work the best. We've had people work by themselves or in teams of 2, but it doesn't have quite the hackathon flavor, and you're not getting as much support from each other as you might. More than 6 people in a team tends to get a bit unwieldy and inefficient. But we're not going to tell you you can't work on your own. We're not going to tell you you can't have a team of 12 people if you have one, but it's just a recommendation. You can come and participate in the hackathon without pitching an idea, without having a lot of experience. There always are teams looking for participants. The hackathon will officially be Saturday and Sunday, August 12th and 13th. We'll start planning the hackathon already on July 11th and July 25th. You don't have to participate in the pitch meetings to be in the hackathon, but if you have an idea and you want to build a team and you want to do a 3-minute mini pitch, we would love to have you do that. So if you have an idea, you want to try it out, that would be great. There are going to be a set of templates and also Google Docs to present your ideas, develop your ideas, organize your teams. And we will work with you to try to identify which ideas are practical. We don't want to tell you you can't do something, but sometimes people come in with fantastic ideas that just don't match CompuCell. Somebody wants to do a molecular docking simulation. Well, that should be done with a molecular dynamics simulator. Somebody wants to do advanced hydrodynamics. You use a package like Phoenix for that. Or they want to do very detailed biomechanics simulations. Probably FE Bio is a better package. And so our goal is not to tell people what not to do, but to help steer people so that that 2 days are as productive and enjoyable as possible, best learning experience possible. A couple of years ago, there was a team that went on to start a company based on what they did in the hackathon. So sometimes these things work really well. A lot of people have started PhD projects in the hackathon. A lot of people have done things that got published later on. On the other hand, it's only 2 days. And so you're not going to finish a project in 2 days. And so we want to help you, guide you so that that experience is as productive as possible. We'll have check-ins every morning and noon. In the evening, we'll ask people to give a brief report on what they achieved or didn't achieve. It's not a graded thing. It's not a course. The goal of all of this is just to help you be productive and help the teams work well. Sometimes teams are a group of people who already know each other very well. That's fine. Again, we'll say you don't have to give a project pitch to participate in the hackathon. There are always people looking for participants. If you don't have an idea and you don't like any of the existing teams, we've found that taking an existing simulation, which was done in a different modeling environment, like PhysiCell or Morpheus or Simune, and then turning it into a CompuCell simulation can be a great learning exercise. Those simulations are often very useful and can be added to the CompuCell repository of models. And so if you don't have an idea, but you want to try a hackathon project and you're looking for something, please come and talk to us. We've got lots of great ideas for things that you could do. Let me just run a quick poll with the people who are here and ask you whether you're thinking about the hackathon. So I'm going to ask you here about your hackathon interest. It's also a first opportunity for people to try out a poll. So please answer this poll. We're just asking you if you think you might like to participate in the hackathon. If you say yes here, you can not participate. If you say no here, you can change and do participate. This is just to get a sense of your interest and engagement. So I do need people to answer that poll before I can move on. If somebody's having trouble using the poll, please let us know, because that's a fundamental part of using the Zoom. And so if for some reason you're not seeing the poll or you're not able to answer it, let us know right away so we can help you, because it's going to be difficult to get through the workshop if you don't have access to the polling in the Zooms. It's possible, but it's not very convenient. Again, this is not binding in any way. If you say you're interested and change your mind, that's fine. If you say you're not, then change your mind, that's fine. Really just to get a sense of where people are. There's still a few people who haven't responded to the poll. And yes, your poll responses are anonymous. We're not going to track you down and say, but you said you were going to participate. You didn't. That's not our goal. Our goal with all of this is just to be as supportive to you as possible. And depending on where you come from, and again, we have people from all over the world. We've had high school students take this class. We've had undergraduates, graduate students, postdocs, junior professors, full professors, retired professors take this class. We've had pure mathematicians take this class. We've had physicists take this class, bioengineers, MDs, surgeons. People come from all over the world with all sorts of backgrounds. And so we want to try to support everybody. And we understand also that sometimes, depending on where you're from, asking questions may not be so comfortable. So there's no wrong question. Don't be afraid to ask questions. It's always okay to ask a question. And don't be embarrassed. We all don't know things. We all make mistakes. You will see me make mistakes. You will hear me say very often, there are things I don't know. You'll hear me say often, people ask a question, I say, I don't know. Don't be afraid to not know. It's okay. We all want to learn together. Okay, great. Let's go on. All right. Hackathon teaming. Please post your hackathon ideas to the Slack. There'll be a Google Doc where you can create a prototype of your hackathon idea. We'll ask you to upload your project pitch, 3 slides maximum, to a file, and then have you walk through it if you're comfortable with that. You don't have to do a pitch to participate in the hackathon, but it's helpful when you're building teams. And if you want to reproduce an existing project, we have some ideas as well. We can work with you offline. During the hackathon, we'd like people to know why they want to do what they want to do, what they want to get out of it. And we need people to have some kind of shareable description, both of the idea and about yourself. What's your background? What are your strengths if you're building a team? How would you build the team? How would you assemble that team? It's fine to be a beginner. It's fine to just say, I'm learning and I want to participate. There's nothing wrong with that. We will do our best to support people during the hackathon. If you're going to do the hackathon, you will need some Python. And so if you can do the Rosalind exercises 1 through 5, which are pretty elementary, that's fine. When you're taking the course, if everything is going well, then the hackathon is fine. Even if things are going less well, and say you're an experimental biologist are in hot demand during the hackathon. People who can read biology papers are in high demand. And so even if your modeling skills are not the best or not so developed, you may still be able to be a very, very strong contributor to a hackathon team. Similarly, if you come from a very mathematical or computer background, you might be able to contribute to a hackathon team really effectively. So even if you don't have everything lined up, don't be shy about participating in the hackathon. Okay. I'd like to go forward now and talking about CompuCell3D. We'll try to get everybody up and running on a very simple CompuCell simulation. This is often a little bit frustrating to begin with. And so if things get stuck, don't get too discouraged. The goal here is to to do debugging and troubleshooting so that when we get to the course proper, everything works smoothly. So if you get stuck, ask for help. We have people here to help, and don't be shy about it. So let me see. Let me just ask you beforehand about the kinds of CompuCell installations and where you are with that. So I have a 2-question survey here. The first question is, are you running CompuCell locally or planning to run CompuCell locally? And if so, is it Windows, Mac, or Linux, or on nanoHub? And if you're using it locally. Is it running for you or not? And if you're running on nanoHub, is it working or not? This will help us get you the support you need. So it looks like most people here today are trying to run desktop. It looks like most people who are running desktop have it working. There are a couple of people with desktop problems and a couple of people with nanoHub problems. The desktop troubleshooting can take time. We may try to set up a session where we can have an open session for people with desktop issues to get together and try to debug. nanoHub this morning was a little buggy, and so we'll see how it goes today. nanoHub is a third-party platform. It has some great advantages. You don't have to install anything on your computer. People have the same interface, and that's wonderful. But we don't have full control over how things work on nanoHub. And so sometimes we get problems, and we will do our best to work around those problems, but as we find them. So we'll see how things go today. Let's come back to CompuCell. CompuCell consists of two main components, an editor called Twidit++, and the main thing to remember about Twidit++ as an editor is that it has what are called code snippets. All of the things that you normally want to do in CompuCell. You want to do something to every cell of a given type. You want to ask a question about all the neighbors of a given cell. There are computational templates for all of those things. And so it doesn't completely write the code for you, but it pre-writes a lot of things that you would have to do, so you don't have to remember them. You don't have to remember, how do I reference the chemical field at a given place? You don't have to remember that. It's in the editor. And in my experience, people don't seem to use that code snippet feature in Twidit as much as they could, and it makes things a little bit more difficult. Player is a tool for running and visualizing and interacting with CompuCell simulations. It allows you a lot of flexibility. Occasionally, it can be confusing or buggy, and so we will do our best to help people if they have issues. One of the nice features of Player is that you can make certain kinds of modifications to the simulation as it's running, which is not that usual in these kinds of simulations. Okay, so talking about installing and running CompuCell, it looks like most people have got it running here. I'll walk through a few things quickly. If people need help, please reach out to Pedro or Giuliano through the chat for help. And we have breakout rooms set up so that if you need to go and work individually on something difficult, you can do it. Probably do not have time to do a new install of CompuCell on your desktop machine during this meeting today. But if that's an issue, please follow along either on nanoHub or just note what's going on, and then contact us for help on the install afterwards. We'll do our best to support you, but it's critical that everybody have working CompuCell before the workshop. During the workshop, it's quite difficult for us to take the time to do install solving, because we've got to support people who are doing the coding itself. If you want to install CompuCell on your desktop, those are available on the CompuCell website. There are recent releases for Mac, Windows, and Linux. Linux people, your life is a little more complicated. We can't always support people who are in strange versions of Linux. Typically, Linux users are pretty sophisticated, so you may have to do a little bit more on your own, but we'll do our best to help. Downloaders have changed for CompuCell. In particular, the Windows installers are different from the old ones. They're a little bit slower. They're supposed to be more reliable, but the command line interface is a little bit unusual. if you're used to Windows installers. And so don't be afraid, do follow the instructions. And if you need help with that, do let us know and we'll try to walk you through it. All of these things live on SourceForge. We should have the latest releases up on SourceForge. You may well find, and people this morning found, that for certain purposes, depending on your computer, you must run CompuCell in administrator mode. You won't be able to run it in user mode. You'll need certain privileges. And definitely a lot of installers these days, because CompuCell is not a registered product, you will have to override the security to allow the install to work on your computer. And if you need help with that, again, reach out to their instructions online, but reach out to Giuliano or Pedro for help. If you've got CompuCell running, the next thing we're going to do is use Twit to write a simulation. And so please launch Twit. You may have to wait a little bit while I walk the nanoHub people through things, and we'll get back to you. You could spend your time looking at the manuals if you like, playing around with CompuCell. Nice thing about software is that it may crash, but you're not going to break anything by making mistakes. So don't be afraid of making mistakes. Running that CompuCell on nanoHub is a little bit more involved, but once it works, it's pretty good. One thing is that, again, nanoHub is a third-party platform, and they managed to break the main version of CompuCell during the last update. That's going to be fixed. We definitely assume it will be fixed by the time we have the main workshop. But for today, we're going to have to do a little bit of a workaround to get you running. And so please be patient and please give us feedback. If you get strange behaviors on nanoHub, screenshotting it and letting us know what's happening is very useful. Some people this morning had a little bit of a glitch that we'd never seen before on nanoHub. And so if we know what that is, we can go to the nanoHub administrators and ask for help. If you really have nanoHub problems, then we will probably try to help you run desktop. Okay, so for nanoHub, the basic place you're going to go is nanoHub. There's a link from the CompuCell website. Normally, we would be using the simulation environment at CC3D base 4X. Unfortunately, today that's not working. Please don't be discouraged. We will get it working before the workshop. And so we're going to do a workaround, which is a tool called Slime Mold that was written a few years ago. It's using an older version of CompuCell. There are a few peculiarities about this, but for today, it's a way of getting things working for the nanoHub. So I apologize if things take a little bit longer, a little bit more, a little bit less convenient today. If people have questions or concerns about that, please let us know, and we'll do our best to support you. Yes, the link you'll be using today is the slime mold link, the last one in the chat. So to log into nanoHub, you go to nanohub.org, hit login. I hope everybody has an account set up. Once you've logged in, it'll give you first, you ask for the login. It'll ask you how to log in. If you're in the US, you would sign in through an affiliated institution. nanoHub can be used from anywhere in the world. Don't have to be US. But in that case, you'd sign in with Google or sign in with nanohub.org account. And so if somebody has a problem getting that set up, we'll do our best to help you out. But this is, again, a third-party execution environment. So I'd ask everybody who can, please either get Twit running on your desktop or get nanoHub launched. And can I ask people to give me tell you what, I'll just use the poll. So I'm going to launch the poll, and please tell me if you have either logged into nanoHub or you have CompuCell desktop Twit running. So please answer the poll. And if you need help, please do reach out to us. Okay, I'll give people another minute or two to try to get in. If you need help, a couple of people said they needed more time. If you're having a problem, please don't wait. Put in the chat that you need help. If you need more time, why don't you raise your hand in the main session? Okay. Once you're in nanoHub, you have to get familiar with navigating. It's not the most convenient thing in the world, but once you've done it a few times, it's okay. One thing you will find in nanoHub is that it does sometimes crash. If your code crashes, don't worry about it. You can restart it. So here I actually have a CompuCell simulation running, but I'm going to hit terminate, which is what you do when things crash. And I'm going to start things over again for you. So in nanoHub, you have something called a dashboard. That is where you navigate. nanoHub is a very old package. And when it was originally released, it was path breaking. These days, it feels a little bit old and clunky because it hasn't changed very much in the past 25 years. But it works most of the time. And it is free and open to everybody in the world, which is pretty amazing. So one of the things, the dashboard will tell you what programs you have access to and what you're running. To get to the dashboard, you can go up to here where it says menu and then click dashboard. You can also go up here to the top left where it says nanoHub, click there and select dashboard as well. Once you've got your dashboard running, and yours will probably be empty, mine has a lot of things in it because I've used it over the years. You're going to want to look for CompuCell. And normally we would go and use the main CompuCell tool, but today, because it's not running, we're going to have to use a special tool as a workaround. So I want everybody who's on nanoHub, if you're using Twit on your desktop, you're done. You don't need to pay attention to this. You can be playing, run some background simulations, find the slime mold simulation and run it. Find the bacterium macrophage simulation. So explore. This will only take a few minutes, but I want to make sure everybody's up to speed. So has everybody got their desktop? Everybody who's on nanoHub, do you have your desktop screen? I'll poll. If you need help getting to your desktop screen, we need to help you out. So let me start this again. Okay. Somebody says okay. Does anybody need help getting here? Looks like we're okay. Great. Okay. So now click on all tools here on the top right. All tools. Make sure the screen share is showing. Yes, showing that. Click on all tools here. And in the search, type the word SLIME, slime. Okay. Everybody got that? It will pull up something that will say CC3D slime mold simulation. Click the little heart to bookmark it. And then click this icon here that says launch CC3D slime mold simulation. Okay, and I'm going to do another poll and make sure everybody's gotten this far. Again, if you're running desktop, you don't have to do this. This will just be for the nanoHub. Once we get everybody up on nanoHub, then the desktop people, the nanoHub people will have the same experience, but we've got to get that started. Okay, you'll get a little warning message. We'll click OK. Don't be afraid of warnings. If you get a warning message, just keep going. And you should get something that looks like this. Did that work for people? If anybody did not get that, let me know. Some people had some odd redrawing issues today in the earlier session. I want to make sure everybody has that. Okay. Now I'll show you a few things about manipulating CompuCell. It's mostly the same on nanoHub and desktop, but not quite the same. You have this bounding box, and you can resize by pulling the bottom right-hand corner. If there is a drawing problem, a screen update problem, changing the size of the bounding box will force a redraw. That normally will fix the problem. You can change the size of your simulation inside the bounding box by pulling on that bottom right-hand corner. Within the viewing window, you may get something like this where you don't see anything. You can have CompuCell relay out that window by going to Window, Tile. That's one of the single most useful things you'll run into in CompuCell Player. And unfortunately, that's not available in Macs. For some reason, Mac OS does not allow that functionality. It does work on Windows. It does work on Linux. And when you lay it out, you should now see the simulation. Is anybody having trouble with that? I want to make sure everybody has that. Now, this is for today only because this is specific to this simulation. You'll see simulation type. I'm going to pull down that menu, and I'll select the first one, which is maze. And this will actually start the simulation. And this is actually quite an interesting simulation to play with. And so if you're waiting for other people, I strongly advise you to play with the simulation. It's actually a very beautiful simulation of slime mold moving through a maze based on a famous paper about 15 years ago about how slime molds, which are unicellular organisms, can solve complex problems in the environment. So people should see this running. And I want to make sure that everybody has that before I go on. People have that? Again, if you're on desktop, you could run this simulation if you like, but you don't have to. Okay. Now, for both desktop and Windows people, I mean desktop and nanoHub people, you'll see 3 red buttons at the top. I see blue buttons at the top. Stop button, pause button, and step button. You'll use these all the time when you're using CompuCell. When a simulation is running, if you hit pause, it will pause it. And I can restart it either by hitting step, which will advance the simulation 1 time step, or run, in which case the simulation will run continually. If I hit stop, that will terminate the simulation and I cannot continue it. I have to start again from the beginning. So in general, you don't want to use the stop function very often. You'll primarily use it when you've changed your code and you want to run different code going forward. Now we can get to the work of running a CompuCell simulation together, writing and running a CompuCell simulation together. What we're going to do is we're going to launch the editor, and we're going to use the wizard, which is a configuration package, to build a simple simulation. The first thing we're going to have to do is launch the editor in nanoHub. Again, if you're online on a desktop, this isn't a problem. In nanoHub, you can launch the editor here with Start Twidit, or go under File and hit Start Twidit. So please start Twidit inside of nanoHub if you don't have it already. And you should pull up a new window like this. You'll notice that there are 2 tabs at the bottom of the screen. On desktop, these are separate applications, and you switch back and forth between them as separate applications. In nanoHub, there are tabs within a single application. Here is player, and here is the editor. In nanoHub, if for some reason things crash, which happens, go up to the top here, hit terminate. It'll take you back to your desktop and restart. Okay. Does everybody have that working? Does anybody have a significant problem with this at this point? Okay. So now I hope everybody has Twidit, and I'm going to walk you through this. Again, you can, if you get screen draw problems, move the cursor bottom corner. So we're going to run Simulation Wizard. I will walk you through the steps once, just verbally, and then I'll go back and we'll do it together, okay? So what we're going to do is we're going to launch Wizard. To do that, we're going to pull down CC3D project, new CC3D project. That'll be our first step. The second step will be we will give the project a name, and we will have to select where to put it. And you'll have to select a place where you have write privileges. Now, if you're on a Windows machine, that almost certainly happens automatically. In nanoHub, you will have to point to your user directory. And in a Linux machine or Mac, you'll have to select a directory where you have write privileges. If you try to write to a directory which you do not have privileges for, like a root directory, CompuCell3D will crash and often will disappear. And so if you start writing a simulation and Twidit disappears, the usual reason for that is that you're trying to write to a directory that you don't have access to. You'll then create the simulation by hitting next. You'll define the size of the simulation. We'll accept the defaults. Hit next. We will then specify the cell types. by typing in the names of the cell types and hitting add. We'll skip the chemical fields. We won't use chemical fields today. We will give the cells their behaviors: contact energy, growth, mitosis, and volume. We'll create the simulation, and then we'll look at what we got. Okay? So now we'll go back and do that together. And please do slow me down, stop me in the chat if I get too fast. Everybody should follow along. So, step one, we're in Twit, whether desktop or nanoHub. We are going to select CC3D project, new CC3D project. And we get a dialog box. Everybody do this with me. CompuCell3D simulation wizard. And if anybody is an experienced GUI programmer and wants to help me expand Wizard to make it better, I would love to have somebody do a hackathon project on that. That's very codey, but we really need that help. The simulation name can be my first simulation. It could be new simulation. I have to give it a new name because I do so many, so I'll say new simulation 6. Because this is a Linux backend, no special characters in the name, no spaces in the name. Don't start the name with a number or a special character. Okay? So pick your name. New simulation 6, my first simulation. Everybody got that? If I'm going too fast, you can just put up a red sign saying slow down in the Zoom. Okay? Now, we have to put this simulation somewhere. We will hit browse. In nanoHub, I will select, it says computer, I cannot write to the root directory. I will select Glazier, my home directory. Choose. In your case, if you're on nanoHub, it'll have your name. If you're on desktop, pick any directory you like that you have write access to. Okay. Everybody got that? And now I seem to have a problem. Which is that the size of this box was such that I couldn't see the next button. Sometimes sometimes nanoHub has problems with size. If that happens, try expanding the size of your bounding box. Okay, I've created my simulation. I hit next. And now we have general simulation properties. This would specify how big the simulation is and its boundary conditions. We're going to accept what we have. So hit next. Does anybody need more time at this point? Don't be shy. Everybody was able to walk through those steps, okay? Okay, now we're going to create our cell types. Again, no special characters, no spaces. We can just call it cell 1, hit add. Cell 1, hit add. Cell 2, hit add. Okay. Everybody got that? You could call it A and B. Anything as long as the names are different. Don't start with a number and don't have spaces or special characters. Hit next. It asks you about chemical fields. We don't have any, so we hit next. And now the critical thing, which is what are the behaviors the cells have? We want the cells to stick to each other, so we select contact. We want the cells to grow, so we select growth. We want the cells to divide, so we select mitosis. And we want the cells to have a defined volume, so we hit volume local flex. And I'll give people a second to get through that. And I'll run a poll. make sure everybody's caught up. Okay. So somebody said they need more time. If you could put in the chat what you need help with, that would be very helpful. We can go over the whole thing again if you need it. No problem. So if you want me to walk through all the steps again, I'm happy to do that. Just ask. Don't be shy. If you're finding it's too fast, that's fine. Just ask. Other people will be finding it too fast. I'm happy to go over these things as many times as needed. The goal is to make sure everybody gets to go through this exercise together. Okay, there's a question about the sizing of the next button. Yes. So if you're having trouble seeing the next button, try resizing the window. Does that work for you? It says it won't let me. You can't grab the bounding box. Try jiggling the outer bounding box there, which will redraw the screen. See whether that helps. Well, that's a workaround I didn't know. Let me try that. So you hit Alt and click in the window. Ah, yes, that works. Thank you, Hayden. I didn't know that. Did that work for you, Elizabeth? Great. Yeah. nanoHub is great in some ways and can be quite frustrating in others.
I had to figure that out myself last night, so luckily, just in time.
We should document that one. That's a great workaround.
No.
I mean, because there ought to be some way to just hit. I mean, in principle, this is N, so something like Command N should work to advance it. So we should find out whether that works. In other words, underscore, it says underscore N. So I think Command N, or I don't know whether it's Alt N, Function N, Window N, Apple N. One of those should actually do it without having to hit the button. So somebody want to explore that while we're waiting? That would be great. People who are on who are ahead can try that out. Okay, let me know. Okay. Everybody got the 4 boxes ticked: contact, growth, mitosis, volume, local flex. Hit next. It'll say configuration complete, finish. Okay. You should see this. Does everybody see this? Maybe I should be saying, does anybody not see that? If you don't see that, let me know, because we need to have that working. Anybody need help? Okay. So now we are inside the simulation. The simulation is complete. Now, most of the time you would have to edit the simulation to make it work, but this one I selected specifically so the raw simulation out of Wizard will run. The simulation is here. If I double click on the name of the simulation, it will open up the details. And you'll see 3 tabs: new simulation.xml, new simulation.py, new simulation steppables.py. We can save the simulation by hitting this double floppy disk icon, very obsolete icon. Make sure that that works. And now let's try running the simulation. To run the simulation, sometimes you'll see the CC3D icon here in blue, and you can hit that, it'll run. But the normal way to run it would be to hover over new simulation. You can also run it. You can also run it through CC3D project, open in player here. But the normal way we launch it is to hover over the name new simulation.cc3d, right click, and say open in player. So everybody got that? And hit open in player. On nanoHub, it will say that there's an existing simulation running. And we'll hit yes to stop the existing simulation. On desktop, depending on what you were doing, it might say that or not. Either way, say yes. Now you need to switch to player. Desktop, you switch applications. On nanoHub, you switch tabs. And now I should have the old tab. It's still showing the old simulation. And now I'm going to hit step. And it should launch the simulation, the new simulation. Again, use that tile function to lay out your screen. So I want to wait, make sure everybody has this on their screen. Some people had some strange nanoHub errors earlier today that I'd never seen. And so if you're having nanoHub problems, I want to make sure you walk through it. Okay. So I'll wait until everybody gets to this point. Okay, I'll do a new poll. See whether everybody's with us again. Okay, so there are a couple of people who say they need help. Elizabeth, you say it's frozen. Does that mean it's not doing anything, or does that mean that it crashed? The simulation will not be running if I hit step. It will just do one step and then stop.
I think it's that bug that I showed earlier.
The windows are frozen. When trying to resize, it won't let me switch to visualization tab. So unfortunately, that may mean that the instance has crashed, in which case hit terminate here and restart the simulation. And let me do this with you. For people who have it running, hit play. And then I recommend hitting visualization here, or hitting this button that's called configuration, and begin to play with how to change the visualization of the simulation. Okay, so let me try to help Elizabeth, and we'll come back together. Okay, so people, please do that while we're doing this. So Elizabeth, if it's really dead on you, I would hit terminate here. Will just terminate on the top work for you? Hit terminate. Okay, and now I'm going to try launching it again. And there's this annoyance at this point that I have to, I just hit the wrong button. I just crashed my own CompuCell. Okay, let me do that again. That's a bad GUI design on our part. That's there are not many buttons you can hit that will crash CompuCell, but there is one And it happens to be in a place where it's easy to hit. Okay, I'm going to go to Windows. I'm going to go to Tile. I'll go to Resize so I can see what I've got here. I'm going to start my simulation. I'm going to pause the simulation. And now I'm going to launch Twitter. Now, if I have an existing simulation to load, I hit this up arrow, Open CC3D project. Here's the simulation that I just wrote. So if I hit open, it should restore what I had before. Did that work for you, Elizabeth? If that went too fast, let me know and I'll go over it again. Okay, to open an existing simulation, do you have Twidit running? Hit Open CC3D project. Okay. Okay, you don't have Twidit running. So we're in slime mold. I have to start the simulation by pulling down here. Here, I'm going to step the simulation. And then I can pause it. Then I have to go back to Twidit, start Twidit. In this case, Twidit's already running, so I don't have to start it again. Can you get back to Twidit okay now? Okay, great. Okay, I go to new simulation. I'm going to relaunch in Player. Always remember that tile function. It's very useful. Does everybody have this now? Everybody together? Great. Okay. Again, you can resize, redraw, and in Twidit, you'll be redraw. In nanoHub, you'll be doing that resizing a lot to redraw the screen. Again, start, run, step, pause, stop. Buttons. Okay, so you wrote a simulation. Let's run it. I'm going to zoom in. You can use your cursor, your mouse scroll to zoom in. I'm going to zoom in and run this. You'll see the simulate cells are growing, dividing, and when they divide, they change type. This is actually a pretty decent cancer simulation. Start. And now at the end, I want to walk you through a little bit of what the code looks like, just a taste before we finish. And don't worry about the details. We'll come back. CompuCell simulations have two components. They have an XML specification and they have a Python specification. XML specifies static things like how many processors am I using? What's the name of the simulation? How big is it? The Python specifies dynamic things, changing things in the simulation. If we come back to Twidit, we see a bunch of tabs at the top that let us navigate between the different components of the simulation. You have a scroll bar here. You can scroll through the simulation. We have our save button. And up here in view, we have a variety of zoom in, zoom out to change the font sizes and things like this. Occasionally, especially if you're interacting with Zoom, you will get a funny error, not particularly in nanoHub, more on the desktop, where the line drawing in Twidit will be wrong. If that happens, click zoom out repeatedly, and that should fix the problem. If it doesn't, let me know. We'll try our best to fix it. There are a lot of display options that you have. Inside of the CompuCell simulation, let's look at the XML. There is a block of code which says what version of CompuCell you're running and the basic properties of the simulation. How many processors, because CompuCell is multi-threaded, so in principle it runs in parallel automatically. And how big the simulation is. For example, the dimension of the simulation is 256 by 256 by 1, 256 by 256 by 1. How long the simulation runs for, and so on. The next block of code says what kinds of cells we have. Medium, cell 1, and cell 2. The next block of code specifies what the cells do. So, for example, we've said that the cells adhere to each other, and contact energy specifies adhesion between cells. And here, by default, the contact energies are all the same. The cells are all identical in their properties. That's something we typically will change. We'll edit that by hand. We can change those things as the simulation runs if we go to the model editor in the player window. So we can change adhesion between the cells during execution of the simulation. The last thing that we might see here is something called uniform initializer. That lays out the initial configuration of cells. CompuCell doesn't have the best set of options. You can draw a square of cells or you can draw a circle. If somebody wanted to write some extensions to that, we would love to include them in the base CompuCell package. Basically, it says a square box, X, Y, lower left corner, upper right corner, how big the cells are and what cell types are included. You can definitely change that. You've changed this value from 51 to 64 here. You can try that and run it if you like while we're talking. You'll see instead of having a lot of cells at the beginning, you'll just have a few. So you can get familiar with that. In the Python, you'll see some boilerplate imports, classes, and so on. Inits, we don't worry about that for now. You'll learn about that. But you'll see some basic things. You'll see a start function, which is initializing the code. For cell and self.cell list, just something to every cell in the simulation. We set the cells a target volume, what volume we want them to have, and how much compressibility they have, how rigid they are when we push on them. We want our cells to grow. Step function is executed every time step. We say that the target volume of the cell increases by 1. Plus equals increments of value by 1. Plus equals 1 increments of value by 1 in Python. So our cells are now growing. And you could definitely change the growth rate, say make it 0.05, half as fast. We want our cells to divide. Here we have the concept of a Python list. We create an empty list of cells to divide. We go over all cells. We say if the cells are bigger than some threshold, 50 in this case, we say divide the cell. Then we loop over the cells we're going to divide. If they are going to be divided, we divide them. There's a function that does that. When a cell divides, we create a new cell. So we have to say what happens to the old cell, the parent cell. And here we say that the parent and the daughter cells both have half of the initial volume, and otherwise the daughter cell is the same as the parent. except that if the daughter's parent cell was of type 1, we make the daughter of type 2 and vice versa. So if the cell was blue to begin with, it becomes yellow after division and vice versa. So we'll see flickering of the cell type. And that's all there is to the simulation. So why doesn't everybody try running it again? See if it works for me. Yeah, okay. So this is a bug in the old version of CompuCell that we're using, which you won't have when we have the newer version installed. So in this particular old version of CompuCell, sometimes when you restart a simulation, it'll load not the current one, but the previous one, which is what's happened to me. I'm going to hit stop. I'll restart. Recent simulations. Project. This, I'm afraid, is a bug that we have to deal with, and it'll be fixed by next time. I'll do open in player again. If you're on desktop, you shouldn't have this problem. Yeah, it crashed on me. So I don't want to take up your time on this. I apologize for this issue with nanoHub. Are desktop people having it work okay? Is anybody on desktop having a problem with it? How about nanoHub? How many people on nanoHub got it to work? Yeah, I'm going to have to relaunch this. Again, the reason we're doing this today is so everybody figures out the bugs, so that when we get to the real course, we've gotten past all the bugs. Yeah, it really doesn't want me to do that, does it? Quit it. Quit it. Open. New simulation. Open in player. Play. Let's see if it works. Yeah, this time it worked. A nice, useful feature in the player is if you hit R, it resets the window. Remember, I started with fewer cells, so now I only have 3 cells at the beginning. I'm going to hit play. We'll see the cells grow and fill the screen. Okay. Everybody get something like that to work? Anybody stuck? So, preparation for the class and the hackathon. Make sure that you can get CompuCell running, whether it's nanoHub or CC3D local. If you're having strange nanoHub problems, we'll try our best to get you a local install. We're working to get the updated version of CompuCell working again on nanoHub. We'll have that. Make sure you can load, edit, and save a simple simulation using Twit, the way we've just gone over it. Strongly encourage you to load and run some of the CC3D demos. CompuCell comes with a bunch of demonstration programs. In nanoHub, they're in CC3D demos. Local machine, they're in your install folder /demos. There are lots of interesting ones like steppable based mitosis, angiogenesis, and delta notch are all really interesting. take a look at the background reading and definitely look at those cheat sheets we provide. If you haven't used Python, do a little bit of Python background. And if you're interested in Hackathon, please do let us know about your Hackathon interests, and we'll do our best to support you. That's all I had for today. Thank you for being patient with me. Are there any questions before we break for today? Okay, well then I want to thank, sorry, okay. When I hit open in player, it's not working. Can you tell us a little more about what's going on? Krishna. First, are you on nanoHub or are you on desktop? Okay. Yeah, that's a good point. So because this slime mold application isn't really designed for editing, we're having to trick it a little bit to allow you to run the editor. If it's really dead, then my suggestion is hit terminate and restart and see if that works.
Yeah, I would suggest terminating. Some people had the issue of nanoHub not allowing switch between windows. So in this case, you have to terminate.
Did that work for you, Krishna? I realize that it's a couple of extra steps. Okay, let's see what I got. I realize it's a couple of extra steps, which you won't have to do when we have the regular CompuCell running on nanoHub. It's just for today that we have to deal with this. Are there any other questions from people? Elizabeth, is it working for you okay? There are a lot of things that you can do to play here. So if you have things running, you can go to visualization, you can change the visualization. You can go here to settings, configuration. And for example, under cells and colors, I don't like yellow and blue. I want one of my cells to be green. So I can change the cell colors. There are a lot of fancier things that I can do too, but that one is a simple one. I can move things around. I can zoom in, zoom out. CompuCell simulations are intrinsically 3D. This is a slice, essentially. A 2D simulation is essentially a thin slice in 3D. So I can actually render this as 3D. And if it were 3D, I could actually see what it looks like. Well, it's not very interesting because it's a 2D image, but I can actually explore the 3D characteristics of it as well. Okay. Is there anybody else who has any additional questions for today? No? In that case, I want to thank you. I realize that there's always a bit of teething problems at the beginning, but once we get everybody running, I think things will be much smoother. The point of today is to get all the bugs worked out so that when we get started and seriously, everything works smoothly. Thanks everybody for coming. Bye.